The point of this first exploration is to show that no matter how curvy a function can look, if you zoom in on a particular point, like 0, 0, and you just keep zooming in, as long as the function has a derivative at that point, or basically a tangent line can be drawn at that point, it will start to look linear. As long as you're zooming in far enough, and as long as it is possible for a tangent line to be drawn. So estimating the slope from this function at 0, it looks like the slope is about 1. If you're to do rise over run using this window here, which means that if the slope when we zoomed in super far is 1, that means the slope of the tangent line at x equals 0 is 1. And then if we're writing an equation of a line, remember, equation of a line requires two things. It requires slope and it requires a point. And so if we're writing an equation of the tangent line, we need to know the slope of the tangent line, which we just said in part B was about 1. And the point at x equals 0, we know x equals 0. And from the graph, we can tell that our y value at 0 is also 0. Or we could plug that into the function sine of x. Sine of 0 is 0. That's another way we can get that y value. So the equation at this point in slope would be y minus 0 equals 1 times x minus 0, or just the line y equals x. In this next exercise, we're going to practice drawing tangent lines at each of the points shown. So like in box A, at point A, we are going to have a very steep positive slope. I'm actually really bad at drawing tangent lines, especially on the device I'm using, but I'm going to do my best. At B, this one's an easy one, horizontal line there. And at C, we've got a slightly less steep slope than at point A, but negative here. In box B, at point A, we have our tangent line. Because that's a straight line, our tangent line is just going to model the slope of the line at point A because it's on a line. So we have a constant slope there. Same with C. So because the slope here is, what is the slope there? Is that 2? Yeah, up 2 over 1. Then the slope of the tangent line at C is also 2. In A, it would be negative 2. Now, at point B, we cannot draw a tangent line here. So remember, the whole point of tangent lines is it's modeling what the slope is doing at a particular point. And at point B, to the left of point B, there's a very clear slope of negative 2. And to the right of point B, there's a very clear slope of 2. So our slope is not approaching any number at point B. It's making an abrupt change from negative 2 to positive 2, which means we can't estimate what the slope is doing at B because they're not approaching the same number from both sides, just like a limit. Remember, slope is like the limit of the slopes of the secant lines. But we make an abrupt change here, so we can't find the approximate slope at B, which means a tangent line cannot be drawn. Over in box C, we can draw a nice negative, oh my goodness sakes, not steep at all line. And at point C, it's positive. But again, at point B, just like in box B, point B, where we have a drastic change happening there, our slope is not approaching. Well, actually, it kind of is approaching the same number, or opposite. So on the left side, our slope is getting steeper and steeper and steeper. And same with on the right side. But on the left side, it's getting steeper and more negative the closer you get to B, and on the right side, it's getting steeper and more positive as you get closer to B. So they are not approaching the same number, so we can't estimate a slope at B, which means we can't draw a tangent line at B. And then point A, this is kind of a funky one, but our tangent line would be a vertical line. What's happening at point A, that's called a point or an inflection point. And it's where the graph changes concavity. We'll talk about what concavity is a little bit more later on. But what you need to know for right now, concave up means, well, I basically think of it as a parabola, and concave down I think of as an upside down parabola. But what concave up means is if you read this parabola or read the slopes of this parabola from left to right, we're going from, at that first point, a very, very negative slope to a less negative slope to a less negative slope to 0 to a positive slope to a more positive slope to a more positive slope. So like if I were to assign like actual values here, we could say the slope up here is like -5, -2, -1/2, 0, 2, 5, 7. I'm just totally making up those values. But basically, if you read that from left to right, our slope is getting bigger and bigger and bigger. We went from negative to positive, and then it's getting steeper and steeper and steeper. Concave down is the exact opposite. If you were to estimate slopes at each one of these points, and then we'd be getting, they'd be decreasing from left to right. So when our slope is decreasing, that's concave down. When our slope is increasing, that's concave up. Again, we'll talk about that more later. What you need to know for now is that if a graph is concave up, all the tangent lines to that graph are going to be below the curve. And if it's concave down, all of your tangent lines are going to be above the curve. At a turning point, or a maximum or minimum of a graph, the slope of the tangent line is 0, or a horizontal line. We can see that in box A, letter B. We went from increasing to decreasing, and where it switched from increasing to decreasing, we have a horizontal line there. The slopes were approaching 0. At a point of inflection, that's where the concavity changes. The tangent line is vertical. And at a sharp corner or cusp, the tangent line does not exist. There is no tangent. So that's like points B and box B and box C. Box B, that's called a sharp corner. The slope changed very abruptly from -2 to +2. That's a corner. And in C, that's called a cusp. At a point on a linear function, the slope or the tangent is the same slope as the line. For our absolute value function in box B, I said a line. I need to be more specific. It's the line, whatever the line is. So in box B, that's an absolute value function, but if you only look at like the right side of the graph, that's a line. It's linear. It has a constant rate of change. That means no matter where you draw a point on that side, they're going to have the exact same when you draw the tangent line to any point on that side of the line, the slope is going to be the exact same. It's going to be 2, just like it is at C, and just like it is for the whole line. Same with on the other side, but the other side would be -2. Anytime you have a straight line, the slope is going to match whatever the slope of that line is. All right, so practicing a little bit more with what we did in the last couple lessons. So our rule, I'm going to jot it down before we dive in here. So difference quotient, oh, it said difference quotient. I was not using the difference quotient. It says at x equals 9. This is my preferred method when we're doing it at a specific point, is to do the limit as x approaches that point. I'm just going to roll with it. So we have the function square root of x minus the function at a, or in this case at 9. Square root of 9 is 3. All over x minus that x value, which again is 9. If I were to plug in, directly substitute 9 right now, I get 0 over 0. So we need to multiply the numerator and denominator by the conjugate. And when I do that, I get the limit as x approaches 9 of x minus 9 over x minus 9 times the square root of x plus 3. We do not want to multiply out the denominator. Our x minus 9's cancel. We're left with the 1 in the numerator. Now when I directly substitute that 9, I get 1 over the square root of 9 plus 3, or 1/6. So the slope of the tangent line at 9 is 1/6, or we say the derivative at 9 is 1/6. Write the equation for the linear approximation of f near x equals 9. So equation of the line, focus on that part. So we've got the slope, now we know is 1/6 at x equals 9. Now we need the point at x equals 9. Obviously x equals 9. And when we plug that into the function, square root of 9 is 3. And so our linear approximation, or the equation of the line there, is y minus 3 equals 1/6 times x minus 9. So if we use that equation, so let's draw what's happening here. We have this, oh, actually we graphed the function on the next one. So let me do that first so you can see what's happening. So square root of x is our function. We've got points out 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. There's our square root function. And we're looking at 9 specifically. And we're drawing a tangent line there. So I could look at this graph and try to estimate using my line what 9.1 is. So really close to 9 there. Or I can plug that in, much more accurate to plug that into the equation. So 1/6, our x will be 9.1. Because we're estimating the value for the square root of 9.1. Our function is y equals the square root of x. So we're basically saying x equals 9.1. 9.1 minus 9 is 1/10, or 0.1. It says don't use a calculator. So we'd have 1/6 times 1/10 plus 3, which would be 1/60th plus 3. 3 and 1/60th. Would be our estimate for 9.1. So looking at this picture now in part D, we want to know, is that estimate an overestimate or an underestimate for what the square root of 9.1 would actually be? So if we look at this graph, we found the equation of this tangent line. We plugged in 9.1 to the equation of that tangent line, and that's how we got 3 and 1/60th. But based on this picture, we can see that our tangent line is above where the graph actually is. Because the graph is concave down, our tangent line is above it. So basically that means that what we got for part C was an overestimate. because the graph is concave down, our tangent line is above it. So if we're going to plug something into that equation for that tangent line we drew, we're going to come up with an overestimate from what it actually is. If you use your calculator to actually calculate the square root of 9.1, you get about 3.0166, which is actually exactly, well, if you round to 4 decimals, is the same thing as what we got in part C. So really, really close estimate. But would it work to use that same formula? So that formula we got was y minus 3 equals 1/6 x minus 9. Would it be appropriate to use that equation to plug in 25? And the answer here is no, because if I were to extend this tangent line and just make it keep going forever and ever and ever, the further I get away from 9, the less accurate my estimates would be. So at 25, right, we know the square root of 25 is 5, but if I plugged in a 25 into the equation we got at 9, I'd have y minus 3 equals 1/6 of 16. What is that? 8/3 plus 3. Oops, don't really want to do that. So 2 2/3 plus 3. I would get 5 2/3 instead of 5, which is not very accurate. It's pretty far off what the square root of 25 actually is to get 5.67 instead of just 5. So the further away this number is from 9, which is where our tangent line was based, the further away our answer would be. So if you're trying to approximate values, you want to make sure you're using a tangent line that is close in proximity to the value you're trying to find. This is the thing we'll end with. So we're going to draw a tangent line at each one of these points, estimate what that slope is, and then write an equation of the line, basically. So at point A, if I'm drawing a tangent line here, I'm not good at this. Okay, that's not too bad. So I'm getting about a rise of 1, 2, 3, 4, 5, 6 over 1, a -6 slope about at A. Oh, is A -3? Yeah, that was at -3. So A is at -3. It's the point -3, -3. I got a derivative estimate of -6. So slope of the tangent line was about -6. Function behavior, that means increasing, decreasing, or constant. So our slope is negative, so that's a decreasing. The function is decreasing there. And then writing the equation of a line. So this is where we're just using that information and plugging it into point slope form. So if I were going to write an equation of that line, now I know the slope, I know the point. My equation would be y plus 3 equals -6 x plus 3. So at -2, -2 would be B. Here's -2, B is down here. That's a turning point, so our slope is 0 there, which means our function behavior is constant. B is the point, not 0, -2, 1, 2, 3, 4, 5, 6, -2, -6. And so our equation there, because our slope is 0, just be y equals -6. C, at point C, which is when x equals -0.5, that's a positive slope. My line is not very straight. Let's try that again. Let's see. I'm getting about 2 over 1. Let's see, is that 1/2? 2 over 1/2? 4 maybe? Point of tangency, C was at -1/2, -2. It's increasing there. The slope is positive. And then we just plug it into the formula. plus 1/2. I'll stop there. The others are pretty similar.